come a long way from the traditional outhouse, along with its associated problems and lack of sanitation. But with the evolution of domestic waste disposal, water became a natural vehicle for transporting waste to someplace else and letting somebody else deal with it. Now, the collection and movement of wastewater to a treatment facility is necessary and is accomplished with a complex system of sewers, pipes, and pumps. But the comprehensive method of handling wastewater consists of three major components: collection, treatment, and disposal. The network of pipes and collection devices carrying waste to the treatment plant is known as the sanitary sewer. Storm runoff from streets, land, and rooftops is collected separately in a storm sewer. Flow from the storm sewer can usually be discharged into receiving waters without being treated. In some cases, a combined sewer is used to collect and move both sanitary wastes and storm runoff. However, during a storm, a plant receiving flow from a combined sewer may be forced to bypass a portion, allowing untreated waste to be discharged into receiving waters. Even cracked or broken pipes can permit infiltration of storm runoff into sanitary sewer systems and overload a plant's capacity. Fortunately, many sudden demands on a plant capacity can be anticipated and explained. That's why it's important for a plant operator to have a good knowledge of the community, including its seasonal industries and lifestyles. Because wastewater needs a natural downhill slope in order to travel to the plant, sewer system elevation in relationship to the plant is a critical factor. Sanitary sewer networks are installed with a downhill slope sufficient enough to ensure an adequate wastewater flow velocity. In addition, manholes are installed every 300 to 500 feet to allow access to the sewer system. Obviously, water cannot flow uphill. When sections of a sewer network are at a lower elevation than the treatment plant, or when hills and valleys are in the way, pump stations are needed to lift the wastewater to a higher point from where it can once again begin its downhill ride. Some wastewater collection systems are pressurized. In this case, each individual household or sewer user has their own pump station with a grinder pump. This type of collection system is typically used around lakes or other areas where gravity flow for sewers is difficult. This type of collection system has virtually no problem with inflow or infiltration, but can be intense to maintain with all of the pumps. The length of time it takes for wastewater to reach the plant will affect the plant's efficiency. Aging wastes create anaerobic bacteria. They cause odor problems and make wastewater more difficult to treat. But no matter what the condition of the wastewater, once it arrives at the treatment plant, the collection process has now effectively completed its function. It is here, at the treatment plant, that the wastewater will be treated and returned to the water environment of the receiving waters. And the biosolids removed during the treatment process are treated in solids handling facilities at the treatment plant. The degree of treatment and the number of treatment processes used will usually be determined by the discharge limits as specified in the facility NPDES permit by state and federal authorities. Not all treatment plants are alike, but they do share similar flow patterns in accomplishing common goals. Upon entering the treatment plant, wastewater usually receives
preliminary treatment
that may consist of screening, shredding, and grit removal in order to initially remove coarse material. From there, the wastewater usually goes through a flow measuring device in order to record the influent flow rates and volumes before entering the primary treatment stage where solids will be separated and removed. The wastewater is next exposed to a secondary treatment process. In this process, carefully controlled bacteria within the secondary treatment process consume organic pollutants from the wastewater. Waste material and solids removed during the primary and secondary treatment processes go to solids handling facilities and onto disposal. At this stage, the wastewater may pass on to another biological treatment unit for nutrient removal or a sand filter for fine solids removal. This additional treatment stage is usually referred to as tertiary treatment. Finally, the treated wastewater flows to the disinfection stage. Disinfection kills disease-spreading pathogenic organisms, and this is accomplished through the addition of chlorine, ozone, or ultraviolet light. Only now, after receiving proper treatment and disinfection, can the treated wastewater be released to receiving waters as quality effluent and in compliance with the facility NPDES permit. Now let's go back and take a closer look at each stage of wastewater treatment, kind of a guided tour of a wastewater treatment plant. But again, keep in mind that treatment plants vary in size and equipment utilization. It all begins here at the headworks, where the wastewater enters the treatment plant, and where screening, shredding, and grit removal are performed, and also referred to as preliminary or pre-treatment. First, the wastewater usually passes through a bar screen or comminutor for removal or shredding of larger debris. The bar screen performs a simple but important function. For the removal of large debris at this point protects equipment and reduces the possibility of interference with in-plant flows. A trash rack may also be used in conjunction with a bar screen or comminutor for removal of very large debris. A comminutor or bar minutor may be used in place of or used in conjunction with a bar screen. The purpose of the comminutor is to shred debris that are present in the raw wastewater that have passed through the trash rack. The shredded debris remain in the wastewater for removal in subsequent treatment processes. Another item removed in the pre-treatment stage is grit. Grit is the heavy, usually inorganic material present in wastewater consisting of sand, gravel, cinders, and eggshells. Since grit is mostly inorganic material, it cannot be broken down by any biological treatment process. So it must be removed early because it is abrasive and will damage pumps and related equipment and take up vital space in biological treatment processes. By flowing through a large, narrow trough called a grit channel, the wastewater flow velocity is slowed to 1 foot per second, which is slow enough for the heavier grit to settle and be removed either manually or mechanically. Aerated and centrifugal grit removal units may be used as well. Before treatment begins, it is necessary to know the quantity of wastewater flow so that pumping rates, aeration rates, or other adjustments can be made in the plant. The most commonly used primary flow measuring device is a partial flume. It's a kind of narrow channel which permits the quantity of flow to be determined by measuring the depth of the wastewater in the flume with some kind of measuring and recording device. One reason for the popularity of the partial flume is its smooth construction, which inhibits wastewater particles from catching or accumulating at the inlet, thereby rendering a maintenance-free operation. Now that the wastewater has been properly pre-treated and its volume measured, it goes to a process called primary treatment. The wastewater is now routed into and through a large tank or basin called a primary clarifier. The flow velocity in the primary clarifier is reduced to a fraction of a foot per second, causing the settleable solids to fall to the bottom and the floatable solids to accumulate on the surface, resulting in clarified wastewater. The slow flow rate provides for an adequate detention time, which is the amount of time the wastewater needs in order to receive effective treatment in the clarifier. So quite naturally, the longer the detention time, the greater the solids removal potential. However, too long a detention time can result in septic conditions that could adversely affect downstream treatment processes. Removal of solids will also reduce the biochemical oxygen demand, commonly referred to as BOD. It's the rate at which microorganisms consume dissolved oxygen as they metabolize the waste. Primary clarifiers are equipped to collect and remove biosolids and scum. Biosolids are the settled solids at the bottom of the clarifier, and scum is the unsightly floatable solids which can be skimmed from the surface. Rectangular clarifiers have wooden or fiberglass skimmers, known as flights, which are moved by a continuous loop chain-driven system. The flights skim the surface and push concentration of scum into a scum removal system that generally diverts the scum to the solids handling portion of the treatment facility. The flights continue their travel to the bottom and scrape the settled biosolids concentration into a hopper, where it is then removed and placed into solids handling facilities. Refer to the illustrations in Chapter 3 of your study manual for a complete view of clarifier design. After adequate detention time in the primary clarifier, the now clarified surface water exits by flowing over notched dams called weirs, which are used to control the flow velocity of the treated water. In many plants, wastewater that flows from the primary clarifier goes to a secondary treatment process. This is basically a biological treatment. With this process, the wastewater is exposed to bacteria, which eat the dissolved and non-settable pollutants remaining in the water. Two of the most commonly used biological treatment processes are the trickling filter and the activated sludge process. Let's take a look at the trickling filter. It can be a round or a square bed of material known as media. Effluent from the primary clarifier is spread over the media by a rotating distributor or fixed nozzles, and the wastewater trickles over and around the many faces of the media and is collected in a channel at the bottom of the unit. The trickling filter does not remove any solids with any filtering action. Instead, the bed of media offers an environment conducive of organisms which attach themselves to the media and feed on organic material in the trickling water. Multiply rapidly and consume lots of oxygen, but they get it from the air rather than from the dissolved oxygen in the water. Eventually, the layer of feeding organisms will thicken and begin to break off and become suspended solids in the trickling filter wastewater. This is called humus or sloughings. The effluent from the trickling filter is then sent to a secondary clarifier, where the humus and other remaining solids will be settled out and removed. The rotating biological contactor, or RBC, does essentially the same job as the trickling filter, except that it is configured differently. Here, the media is rotated, while the wastewater is stationary. As the media is continually cycled through the pool of wastewater and open air, organisms are able to multiply and feed on the organic material in the wastewater without consuming dissolved oxygen. An alternative method used in secondary treatment utilizes the aeration tank. When aeration tanks are employed in the secondary treatment process, the plant is identified as an activated sludge plant. The activated sludge plant is probably the most popular biological treatment process being built today. Being a biological process, the activated sludge method performs the same function as the trickling filter or the rotating biological contactor. Effluent from the primary clarifier is piped to a large aerator tank, where air is either forced into the wastewater or more naturally induced by mechanical churning of the tank contents. Aerobic bacteria thrive in this environment and feast on the organic material found in the wastewater. The effluent from the aeration tank is called mixed liquor, and it is piped to a secondary clarifier where the feeding organisms will settle to the bottom while the clear water flows over the top of the effluent weirs and travels to the disinfection facility or on for tertiary treatment. The settled organisms in the secondary clarifier are known as activated sludge. A proportion of activated sludge is then pumped into the aeration tank, so the feeding organisms can be reintroduced into the aeration tank, while the remainder is pumped to solids handling facilities. Whether it be humus or activated sludge that is produced by the biological treatment process, they must not be discharged into receiving waters. Protection against this possibility is accomplished with employment of a secondary clarifier. What about the biosolids? What do we do with them? Where do they go? Settled biosolids from primary or secondary clarifiers are usually pumped into a digestion unit where biological treatment and stabilization of the biosolids occurs. A type of digestion unit that is sealed so that no air can enter is called an anaerobic digester. Anaerobic bacteria will prevail in this process. As opposed to aerobic bacteria, which require dissolved oxygen, anaerobic bacteria thrive in an environment devoid of dissolved oxygen, which is derived chemically from their food supply. The result of the anaerobic bacteria eating the organic material in the biosolids is the production of carbon dioxide and methane gas. Biosolids are generally considered properly digested when approximately 50% of the organic matter has been consumed by this carefully controlled biological process. The methane gas produced is usually used to heat the digester, but strict safety practices are imperative, for when mixed with air, gas from the digester is extremely explosive. Refer to Chapter 3 of the Field Study Manual for illustrations and detailed description of the complete biosolids digestion process. Treated biosolids from the digester are periodically removed for dewatering, processing, and disposal. Aerobic digestion may also be utilized to biologically treat the biosolids removed from the treatment process as well. There's another type of treatment plant deserving mention that does not resemble the concrete and steel structures we've seen so far. They're called treatment ponds or lagoons, and they're specially designed to maximize a special method of biological treatment which is capable of producing an effluent similar to most other types of treatment plants. Economics, land availability, population, and a host of design considerations usually determine the feasibility of a treatment pond. In a later chapter, wastewater treatment ponds will be discussed in detail. Before the treated wastewater can be discharged into a receiving stream, it must be disinfected. Disinfection kills only the harmful pathogenic organisms as opposed to sterilization, which kills all organisms. Sterilization of the effluent is not a function of the treatment plant. A chlorine solution is mixed with the effluent from the secondary or tertiary clarifiers, and the mixture is diverted to a chlorine contact basin or tank. Other types of disinfection processes may be used in place of chlorine. Ozone and ultraviolet light are examples of alternatives to chlorination. Proper mixing and contact time are very important and must be regularly monitored. Now, and only now, after the wastewater has been carefully processed through all treatment stages under the watchful eye of the treatment plant operator, can it be returned to the environment in full compliance with all requirements of the NPDES permit.